Alright, and we're back with day 9, and as you can see the day 10 is about to launch actually in 1.5 hours. Now I don't know if I can probably do both if I finish 9 on time. Right, so let's just focus on 9 then. So what have we got? Rope bridge. This rope bridge creaks as you walk along it. I've never crossed a rope bridge before, now that I think about it. You aren't sure how old it is or whether it can even support your weight. Well, stay away from it then. It seems to support the elves just fine though. The bridge spans a gorge which was carved out by the massive river far below you. You step carefully. As you do, the ropes stretch and twist. Turn back. Why would you continue? You decide to distract yourself by modeling rope physics. Maybe you can even figure out where not to step. Okay, that would help, I guess. Consider a rope with a knot at each end. These knots mark the head and the tail of the rope. If the head moves far enough away from the tail is pulled toward the head. Due to nebulous reasoning involving plank lengths, you should be able to model the positions of the knots on a two-dimensional grid. Then by following the hypothetical series of motions for the head, you can determine how the tail will move. So they're using plank length, just pretending that's a minimum distance, that anything can move, which is not actually true. A lot of people think plank length is the smallest unit of distance. It's not. It's just a unit of distance. Fine. Due to the aforementioned plank, the rope must be quite short. In fact, the head and tail must always be touching and even overlapping. Okay, let's look at the example then, because that's a bit confusing. Alright, so we've got the head next to the tail. The head moves okay, so they're touching because it's adjacent, and diagonally includes counts as adjacent. Fine. If the head is ever 2 steps directly up, down, left, or right, the tail must also move 1 step in that direction so it remains close enough. So if H moves, okay, fine. Otherwise, if the head and tail aren't touching and they aren't in the same row or column, the tail always moves 1 step diagonally to keep up. Fine. So that covers all situations then. I am happy with that. You just need to work out where the tail goes as the head follows a series of motions. Assume the head and the tail both start at the same position, overlapping. The series of motion, so right 4, up 4, left 3, down 1. Okay, so every time you do a move, you just have to work out where the tail ends up, if it even moves. We don't need to create a grid or anything. We can just have pointers to. We could just have coordinates for head and tail. Basically, that's all. count up all of the positions the tail visited at least once. In this diagram, S again marks the starting position, so there are 13. Okay, I get it. So forgot to make a new file. And I forgot to copy the input before the stream. Alright, doesn't look hard, just code it correctly. Keep a set data structure of like all the coordinates that tail has visited. So, whoops, that shouldn't be there. Okay, 9. So we want, where does head start? This starts at oh, they don't actually give us coordinates, alright. So we can just say it starts at 0, 0. Yeah, okay. Head. So should we just say hx, hy equals 0, 0. Tx, ty equals 0, 0. That's where they start. Yeah, so then we just want to get the inputs. With open input for line and lines. So we want direction dist equals line dot strip dot split. I see. Well, when we, I mean distance, do we just move the ahead one space at a time? I guess we must. Yeah. So we're gonna need to make a let's say right global hx, hy, tx, ty. So it basically keeps track of, oh, and we need a visited equals set. There we'll store all the locations that tail has visited. Does the first one count? Visit. Yeah, it does. Okay. So visitor dot add tx, ty. Okay. So we want to say if we move right by one step, then we want hx equals hx. Oh, okay, do this plus equal 1. That's all. If hx is, so if doing that has caused us to be 2 spaces away from tx, so if hx is greater than tx is 1, yeah, that's then two cases. Either we're on the same horizontal line, so if hy is ty, then we do ty plus equal 1, else we if hi is greater than ty, well, we always, okay, sorry, that should be tx. Well, we're always going to do we're always going to add 1 to tx. So tx plus equal 1. So the only cases we want to additionally check, if hy is greater than ty, we do ty plus equal 1, so we move diagonally. If hy is strictly less than ty, we move down diagonally. So we always move the x by 1 and we move those, okay. And then finally, visitor.add tx ty. That's moving right by 1 step. And then we want to do just copy that for left. So it's just a case of changing the variables again. As always, there's probably a cleaner way of doing this. Do we actually need this? I never remember how to use global correctly. Alright, so we want hx minus equal 1. The better way of doing this would be using deltas and directions, but whatever. If hx is now less than tx minus 1, we move tx. Now if now this stays the same. Okay. Now we want up. So now we're inverting the y's and the x's. So we do if hy is greater than ty plus 1, move ty, and then we handle the diagonal case. It's genuinely just changing y's with x. Bound, so I've got something wrong here. And down, we just change that to minus ty, but less than ty minus 1. Ty minus equal 1. If hx, that will keep the same. Alright, I think that's it. It wants 2 blank lines per. Alright, alright, PyCharm, we'll play your game. So, if so for so we just do this repeatedly for every unit of dist. Is it ever going to be 0? No, it doesn't matter. Alright. If direction is right, is that the letters we use? Yeah. Then we just call right. Left direction equals left, left, left direction equals up, up, left direction equals down, down. And then finally, we just want to see how many we visited, right? So I've just done everything in one go, which probably means I've done something wrong because I didn't test it as I went along. 6236. Correct. Yeah. There wasn't that much to do. It's literally just moving one step in either direction. A rope snaps. Suddenly the river is getting a lot closer than you remember. Yeah, well, what did you expect? The bridge is still there, but some of the ropes that broke are now whipping towards you as you fall through the air. I don't want to read all of this out. Let's just skim read it. How to arc your body to avoid being hit by the ropes? Are the ropes your concern? What? You must simulate a rope consisting of 10 knots. One knot is still the head of the rope and moves according to the series of motions. Each knot further down the rope follows the knot in front of it using the same rules as before. Oh, damn it. Okay, fine. Now you need to keep track of the positions of the new tail. 9. So we've got lots of tails, but the last tail is what we care about. 9. So H is the head. Okay, fine. Oh my god. Alright then. So we do need a bit of a change here then. So we've got... Okay, we can no longer do this. We need an array. So we need rope, let's say equals... let's say... 0, 0 times 4, 10. Alright. Visited equals, so we want basically tuple of rope. The last entry, that's the tail. Alright, so we don't need this global nonsense anymore. So right, it's, oh man. Alright, so I think we don't actually want a function that moves something right or up or down. What we want is a function that resolves. You've already moved a knot. It's now stretchy, and you want to resolve that. Given the position of one knot, you want to resolve the position of the next knot. And then we can just call that for each knot down the line. So this... Plus, we can do this in a symmetrical way, so we don't need 4 different functions. We can just say, start this from scratch. Just say, okay, so let's say resolve with knot 1, knot 2. So given a knot, or just say head and a tail. So this is like a mini rope segment. Given that we've moved head, we now want to resolve where tail ends up. Alright? So we want to say so basically if abs of head 0 minus tail 0, so that's the horizontal distance, is greater than 1, or let's say if it's less than or equal to 1, and the same for then we return. We don't need to change tail. So we're assuming that we've actually stretched it somewhere. So we need to move tail 1 space towards head. Now if it's on the same horizontal line, we move it horizontally. If it's a vertical line, we move it vertically. Otherwise, we move it diagonally. Interesting. Okay, so there's a clean way of writing this, which actually resolves to a clean way of writing part 1, which I didn't do. So, how do I do this? We want to say, we just want to work out the, okay. H dist is going to be how much we move the tail horizontally. H dist, and that is just, regardless of the vertical distance, it's just no wait, this is not quite right. Yeah, this is right. So our assumption is tail is now moving towards head. So we don't need to see if it's 2 or more spaces away anymore in any direction. So now we know for sure the horizontal distance we move is going to be head 0 minus tail 0. But we want to... But we want to divide that by itself, because we want that to, what am I trying to say, be 1 or minus 1 or 0. Oh no, but that could be 0. Hang on. Okay, I don't know a nice mathematical way of doing what I'm trying to say. If it's bigger than 1, we actually want to bring it down to 1. If it's smaller than minus 1, we want to bring it to minus 1. If it's 0, we want to keep it 0. So we want to say if h... There's probably some mathematical function which does that. Because we only want to move it by one space. So h dist equals... Oh, you can actually do it like this, I guess. Equals min of... No. What am I trying to say exactly? The minimum of h dist and 1. So if it's smaller than 1, it stays put. If it's greater, then it will resolve to 1. Yeah, that's what I want to say. And also, still, there's probably a better way of doing this. That's how much tail is going to move. So we can just do that right now. So tail 0 plus equal h dist. And then just do exactly the same for the vertical distance. V dist. So now we just use the vertical. Why does it add these spaces? Okay, we can leave those spaces in. All right. So now tail has ended up in the new place. That's it. That's the function. We don't do anything else. Okay. Now we have to just say 1, 0. Find the vector. So delta equals 0, 1. Delta equals 0, minus 1. So we do rope 0s, that's the head. The x coordinate plus equal delta x, rope 0, the y coordinate plus equal delta y. So that's the movement, and then we just have to resolve everything that happens afterwards. So we go for I in range. Oh, so we want to start from 0. The final element in the list is 9. That's the tail. But we want to end on I being 8, because the tail just follows afterwards. So we want to resolve. So we want to resolve rope I along with rope I plus 1. So we pull the next knot along if need be. Most of the time, towards the end of the rope, nothing's going to change. You have to really stretch it out before the final tail will actually move. So when we get to 9, it'll be... When we get to 8, we'll move rope item 9, which is the end of the rope. End of the line. And then finally visitor.add rope. Well, it has to be a tuple rope -1. Okay. Does that look okay? 2449. It feels dodgy, like something could way more easily go wrong with this algorithm. But they've got a good test case for us to try out, so got it. That was a good problem, I like that one. It doesn't take long to write. You have to be a little bit smart about it, especially for the second part. Especially if you want to write it in a more sensible way without loads of if cases. I think I got it in the end. I started with a fairly unwieldy kind of set of right, left, up, down, but this is what I should have done from the start. HDIS, is there a nicer way of writing it? I suppose you can take this block, oh, I'm not even showing the IDE. Hang on. I suppose you can take this and like put it in there. Nah, that's just less readable. Is there a sign function? I think what I'm trying to do is take the sign. Oh, it's numpy. It's a numpy thing, but it's not in base Python. Signum. That's what I was trying to find. That brings numbers to either 1, 0, or -1, depending on what their sign. But yeah, I mean, that's basically what you're trying to do. This extends easily to any rope of any length. Nice. Nice problem. I like the possibilities for how you could make this harder, all sorts of weird stuff. It just goes to show how weird ropes really are. Well, how hard it is to model the physics of ropes or things that are pulling other things. I mean, there's the example where you have a ball, no, you have like a pivot and you have a ball on a rope, and then you have another ball on another rope hanging from that. The moment you start it moving, you get completely chaotic, unpredictable motion. If it's just one ball on a rope, then you get simple harmonic motion, which we studied in high school. The moment you have two, you can't easily model where they're going to end up. It's going to be like all over the place. Why did I bring that up? I don't know, because that's not actually what's happening here. There you've actually got gravity. This one's a bit simpler. You can predict the motion at every step. Alright, I'm done. See you. Well, hang on, let's have a look at the calendar. Oh, it's still 50 minutes away. Alright, well, I'll actually restart the stream later, so I'll take a break now. So, see you in 50 minutes. Stop the... Damn it. Okay, there we go.